Right, over the next 20 minutes, I'm going to sketch out the challenges of climate change, which, whilst based on science, whilst based on emissions data, the challenge is still something way beyond anything we are prepared to countenance as yet, both in terms of mitigation and in terms of adaptation. I've called the talk from rhetoric to reality because we're actually quite good at the rhetoric, and I don't mean that to be critical. I mean, actually, we need to have the rhetoric before we actually start to make the actual changes. But we're good at the top-level statements, the high-level statements, the aspirations at the global, national, even at city level. What we're really poor at doing is translating that into the reality, and particularly translating it into the reality today, tomorrow, and the next day, which is the time frame that we have to deal with climate change. So I'm going to try and get that all across in 20 minutes. I'll start off at the city level, the climate change strategy from Greater Manchester. In the core objectives section, you're probably all more familiar with this than I am, it makes a very clear statement as to what Manchester wants to contribute to. Greater Manchester intends to make its contribution to targets set out in the UK Low Carbon Transition Plan. This is the right thing to do as part of the global effort to combat climate change. It goes on to say that radical action on carbon emissions is needed in order to pass a viable and safe climate onto future generations. So there's a very clear statement of intent, direction, and therefore, hopefully, action from Manchester here. But what do we mean by viable and safe? We have to actually frame this, as Nancy was saying, we have to frame it in the science, the social sciences and the physical sciences. We have to provide some quantitative framework to this. This is the Copenhagen Accord from the sort of damp squib of an affair that occurred in 2009. The big benefit of the event then was the lawyers went home early, and this statement came out of it, which hasn't come out of any of the previous negotiations, and actually I think it's the most useful thing to come out of any negotiations on climate change so far. To hold the increase in global temperature below 2 degrees Celsius and take action to meet this consistent with science, quite a radical challenge that really, and on the basis of equity even more so. And we've all signed up to this. All of us here have signed up to this through our governments. Most governments in the world now have signed up to this. So that's a quite clear objective at the international level. And the Manchester strategy makes very clear about its commitment to keep with the UK Low Carbon Transition Plan. So what's that say about our targets? Well, that's very clear as well. To avoid the most dangerous impacts of climate change, average temperatures must rise no more than 2 degrees centigrade. No, it's no more than, not a 50-50 chance of, or a 63% chance of exceeding, which is the budgets from the Committee on Climate Change, no more than 2 degrees C. So we have a very clear set of statements about what Manchester climate change strategy needs to deliver on. The mitigation question is clear. What emission reductions give a good chance of staying below 2 degrees Celsius? But if we fail on mitigation in Manchester and elsewhere around the world, and that is increasingly looking likely, then what temperatures, what climates does Manchester need to consider adapting to? And of course, we have to remember that what we put in place today will be there for the next 50 or 100 years. So anything we build from now on, we have to build that in mind of adaptation. But why 2 degrees centigrade? Where's this magic number come from? Well, I'm going to go through this very quickly. Some of you, hopefully most of you may be familiar with these. They're often referred to as the burning ember diagrams. And it's one of the sort of managerial tools that has been used to basically collect a wealth of scientific literature out there, in this case related to impacts of climate change, bring them together into 5 bar charts that relate to different risk categories, ranging from ones to do with ecosystems over here, through to extreme weather events here, and then large discontinuities, often referred to as tipping point issues here. And the redder it gets, the worse it gets. You've got the temperature along the side. And these impact studies are used to try and decide what sort of temperatures we should be aiming for. And this is where the 2 degrees came out of. This sort of guardrail threshold between acceptable and dangerous climate change emerged out of international negotiations. It's not a scientific threshold. Science can only inform this. It's a political, social threshold. So 2 degrees C rise compared to the pre-industrial periods, brought about through anthropogenic human-based emissions, is the guardrail between acceptable and dangerous. But this set of data was revisited in 2009 using the latest science that we have on impacts, which is actually we're getting a much, much wider wealth of that science now. And as you'll notice straight away, there's a lot more red. And if we plotted what we said was an acceptable threshold there, and remember that we might think it's acceptable. For poor communities in the southern hemisphere, who are relatively powerless, for them it's already extremely dangerous, if not deadly, 2 degrees centigrade. But we've never cared about them, particularly in the past, and I doubt we will do in the future. They have no power. So we've internationally negotiated for 2 degrees centigrade, despite the fact many people will suffer from that. But that's where the threshold is now, if you look at the latest science on this. So the question then has to be asked, is 2 degrees C the threshold between acceptable and dangerous, or actually more appropriately, between dangerous and extremely dangerous? If we want to be consistent with science and logic, which working in the university is something we should be, then it seems reasonable to make that, or at least raise that question, if not make that statement. Is 1 degree C the new 2 degrees C? Well, I think it certainly is. But I'm going to do what the rest of us do and say we'll stick with 2. It's almost too late to stick with 1, unfortunately. But we should accept the fact that we have actually written off some of the southern some of the southern hemisphere communities as a consequence of sticking with 2 degrees centigrade. So what do we see in relation to 2 degrees centigrade? What are the targets that we're aiming towards? Well, these are the sorts of things I think you're probably familiar with. You see them regularly in the press. Large reductions, 80%, that sort of thing, but not in my term of office. Now, we all like this. 2050, the problems can be solved by then. 2030 means we haven't got to change our cars. We haven't got to change where we live. We haven't got to have other people living with us. We don't have to do anything really, because technology in 2030, nuclear power, wind turbines and so forth, that'll solve the problem for us, which will be all well and good, but it has no basis in fact on science anyway. The science is absolutely clear that we are changing the climate in this event today, regardless of what our action is. Those lights, this talk, running the sound system, the energy going into that will be changing the climate around the globe for the next 100 to 200 years. So that's what we're doing today. We're changing the climate for the next couple of centuries. So that tells us something quite clear, that 2050 targets are unrelated to climate change. Despite the fact lots of scientists use them as a shorthand, 2050 targets have nothing to do with climate change, and no one should be referring to them. The only thing that matters from the science on climate change are cumulative emissions, the build-up every single day of emissions. So when these lights are on tomorrow, they'll be putting CO2 in the atmosphere, carbon dioxide in the atmosphere. They will add to today's and add to yesterday's, and that will build up day in, day out into the future. That describes a carbon budget on the long-term target, a completely different way and scientifically robust way of thinking about climate change. The reason we don't like that, of course, is it rewrites the whole chronology. It rewrites the timeline of climate change. It takes us from long-term gradual reductions, nuclear power, wind turbines, lots of things in the future, bits of technical wizardry and so forth, which as an engineer I really like. But unfortunately it takes us away from that to the fact that we need to urgent and radical reductions, way beyond anything we've been prepared to countenance. We've really left it too late, to be honest, for 2 degrees C. That's what the science seems to be pointing towards. A complete change in the policy framing that we don't like. So let's try to think about what that might look quantitatively. When we start to pull this together, what does the scale of the challenge look like for 2 degrees C? Well, first let's factor in the latest emissions. Now, we had the Rio summit in 1992. We've got the Rio Plus 20 summit this year. So clearly, we must have done a lot about carbon dioxide in the meantime. That's the growth rate for the previous 100 years of carbon dioxide emissions, 2.7% per annum. Rio 1992. So clearly, by 2000, we'd have got emissions coming down, or at least the growth rate would have been lower. Between 2000 and 2007, it went up at 3.5% per annum. So the growth rate of emissions is actually going up, despite more and more rhetoric spoken about climate change. Remember, it goes up from a larger number every year. So what's the latest data? Almost 6%. Despite the fact this is the beginning of the economic recession, the latest data is a 6% increase in CO2 emissions. What's the highest emission scenario that anyone's considering? In fact, I think it's the highest emission scenario that fed into EcoCities from UK CP09. It's something called A1FI for anyone who's interested in that sort of stuff. So the highest scenario that almost any organization is considering around the globe, including many of the climate modelers, is A1FI, and that's a 2.2% per annum increase. We haven't had that since the previous millennium, the previous century rather, well, previous millennium as well. So why are we doing this? Why are we actually pretending that we're doing something that we're not? Our emissions now are 2 times higher than the highest emission scenario we're prepared to countenance. So what does our failure, our abject failure to reduce emissions, and the latest science on cumulative emissions, what does that say about this pathway, this 2 degrees C pathway that we've all signed up to? Well, firstly, the earlier we can peak emissions, the lower is the rate of reduction after that emissions. Remember, it's a cumulative problem. And that's why. So we need to peak emissions as quickly as possible. Now, the Stern report, some of you may have heard about, came out in 2006. It assumed global emissions would peak in 2015. Its principal analysis is based on a 2015 global peak. Stern doesn't think that will happen, and I guess that no one else here will either. But it gives you a nice political answer. What happens when you look at 2015? What we've got here are 3 curves taken from a paper myself and a colleague wrote in 2008 for the World Society Journal. We've got an update that came out last year. These are the emissions on the side and the years along the bottom of the century. These are emissions going up as they are now, and then they have to peak as early as possible and then come down. And the cumulative bit is the area under the curve. So forget your long-term targets, they're meaningless. It's that stuff under the curve that matters. And the range of curves just show the scientific uncertainty. Science is always uncertain. If it isn't uncertain, then it's not science. So there's a lot of uncertainty exactly what the budget is, but it's sufficient certainty for us to give quite clear policy directions. And the bit I won't go on about today, the reason it doesn't go to zero, you've got to feed 9 billion people. If you plow a field, you release methane into the atmosphere. If you use fertilizer, you're putting a lot of nitrous oxide into the atmosphere. You start to change the other greenhouse gases. So we can't get down to zero. If you're going to feed 9 billion people, you will always have emissions. And the emissions bit here means you have less there to spend on energy. Now let's imagine we left it till 2020 to peak, and that is still enormously challenging. Remember, the Committee on Climate Change in the UK assumed global emissions peak in 2016, which assumes China and India peak in 2017. Again, totally unrealistic. Yet that's what our policies are based on in the UK. A 2020 peak, what you'll see, it starts to come down a bit steeper. 2025, which is still challenging, but probably just about doable. Look at the speed you have to come down at. This is for a 50-50 chance of 2 degrees centigrade. A 50-50, not stay below. A 50-50 chance of entering extremely dangerous climate change. Let's take away the deforestation emissions, let's take away the food emissions, and the area I'm particularly interested in is energy. So what happens to energy? Given that we're in 2012 now, we've done nothing so far this century but watch emissions rise. Firstly, most of the scenarios are impossible. You've already bust the scenario. We've blown the budget for most of the science. You have to be on the optimistic end of the science. And even if you're on the optimistic end of the science, there's your emission reduction for energy. This is a global one. Remember, if we're going to split this amongst the poorer and the wealthier parts of the world, I think it would not be unreasonable that the poorer parts get a bigger share of this cake than we do. So this is much more challenging for us in the Annex 1, the OECD countries. That's a 10 to 20% annual reduction from 2020 peak. 10 to 20% year on year for a couple of decades. And notice it goes down to zero. That's no gas, no coal, no oil, no shale gas, no carbon capture and storage. You can't get carbon capture and storage down to zero. There's nothing we know that can fit into that except for renewables and nuclear and biomass. And that's to give us an outside chance of extremely dangerous climate change. Now, this all looks a bit challenging, I think probably most of you admit, so let's think of a different future. Let's think of a 4 degrees C future. A lot of people say, well, maybe we should go for a higher temperature. If you go for a higher temperature, you get a bigger budget. It's easier for us. So what's that look like? Well, if we peak in 2020, then we can aim for 4 degrees. We need about a 3.5% reduction rate off the top of the curve. That's doable according to the economists. We can have economic growth and a 3.5% reduction rate. It's never occurred so far in the history of humankind, but the economists tell us it's doable. So the future, this sort of future is possible. We can aim for 4. Is that more realistic? Well, what does 4 degrees C look like? Firstly, it's a global mean surface temperature, which these temperatures you always have to remember. 2 degrees C sounds quite pleasant in Manchester on a cold May morning. 4 degrees C, a global mean surface. Most of the planet is covered in oceans. Water has a very high thermal mass. So the land warms up much faster than the oceans. So you expect to see 5 to 6 degrees C as a global mean on land. Now think of that in the hottest days of the year. These are runs by the Hadley Centre, and again, they should come with the caveat, or there's a lot of uncertainty associated with these, but these are broadly the sorts of numbers that people are talking about. Increase in the hottest days. China, 6 to 8 degrees. So during the heat waves in Beijing, with all their buildings that are the new ones, appallingly built in terms of dealing with heat, 6 to 8 degrees. We come to Central Europe, where about 20 to 30,000 people died in 2003. Add to that heat wave, 8 to 10 degrees. Make those heat waves longer and more regular. Do you think we can cope with our Victorian infrastructure, our urban heat island effect? How are we going to adapt to anything like that? You go to the US, imagine in the subway in 10 to 12 degrees. We might be on the subway, but we won't be going anywhere because we won't be running, nor with a tube. So these are the sorts of temperatures we're talking about. And we're heading in this direction at the moment. In fact, we're heading above this direction at the moment. And this is not for 2100. This could well be 2050. In the poorer parts of the world, you start to see big changes in rainfall, and indeed the heat itself starts having big impacts. So the estimates are that with the staple crops there, you'd see a 40% reduction in staple crops and a 9 billion population. Is that a world you want to live in? Is that a world that's in any way compatible with modern, contemporary, civilized, if that's what we are or what we're aiming for, society? My view from polling the scientists sort of anecdotally over a lot of years now is there is a widespread view that 4 degrees C future is incompatible with an organized global society. We reach for the Kalashnikov rather than the debating table when things get difficult. Is likely to be beyond adaptation and is devastating to the majority of ecosystems, and it has a high probability of not being stable. Once you reach these sorts of temperatures, you're likely to trigger other effects, discontinuities out there, tipping points, as some people call them. So you might go up to a high level, 5, 6, 7, 8 degrees before you stabilize. It will stabilize. We may not be here anymore, but it will stabilize. So consequently, we should avoid 4 degrees at all costs. So we shouldn't go there. We need to hold 2 or 3. But before despairing, have we got the agency? Have we got the ability to make these completely unprecedented reductions and adaptations? Because we're going to see a lot of climate change even if we do reduce. Just to put some numbers on this, a 10% per annum reduction rate requires for the wealthy parts of the world, if not the rest of the world as well here, by 2015, a 40% reduction, a 70% reduction by 2020. It should really be higher than that for the wealthy parts of the world. And basically fully decarbonized for us in the OECD countries by 2030, fully decarbonized, not just electricity, planes, trains, fridges, and all the rest of it as well. Now that's impossible, so we keep getting told. But then so is living with 4 degrees C. So the future is impossible, which is great because that means as researchers we get blank sheets of papers and checks, in theory. So we have to think of a different future. We've got to think outside the box. Everything at the moment tells us the future is an impossible place to be. So what can we do about it? Is there anything out there? Well, I'm going to go through a couple of things quite quickly. Firstly, equity. And I find that quite strange. As an engineer, the idea that equity comes out of this is something that might help us think about how to resolve the problem. I don't say it gives us an easy answer. And the other one is about technology. Firstly, look at the equity one. There are 7 billion people, or probably more than that, and a little bit more than that on the planet. How many of those need to make a change? Remember, we're talking about climate change, not sustainability. If you talk about sustainability, it's a different issue. They're actually quite often incompatible, climate change and sustainability. Of responding to them is anyway. Vilfredo Pareto's rule, as an engineer, rule of thumb we call it, 80-20 rule. 80% of something relates to 20% of those involved. 80% of emissions come from 20% of the population. We know that's broadly right. We see that around the globe. We can see it in our own communities. If you then run that 3 times, in other words, go into that 20% and do the 80-20 thing again, and then do it again, what you show from that, and this is only a very broad sort of guideline, and some of the data we have suggests this is roughly correct. 50% of the emissions come from 1% of the world's population. It might be 40 from 2 or 60 from 1. But it gives you a framing that actually you don't have to put in policies in place for most people around the world, because most people don't emit very much at all. And they won't emit much in the next 10 or 20 years, despite the fact we often hear it's a population problem. It's not for climate change. The question then is, who's in that 1%? Every climate scientist. I don't think there's any exceptions. Every journalist and pontificator on the climate, any academic in the OECD, anyone who gets a plane once a year, anyone earning over 30K, probably considerably less than that in the UK, will put themselves in that 1% category. So when we, probably all of us here, when we either shaved or put our makeup on this morning, we were looking at the 1% person in the mirror. We know who they are. And are we prepared to change our cars, change our fridges, the way we live our lives, where we go on holiday, how often we fly? Are we prepared to change those things now? Have those things forced upon us? I think we know the answer, and it's probably in the word now, but without the W. We're not. That means we are then prepared to hand on to our children, to other people elsewhere around the world, a 4, 5, 6 degree C future. We have that choice. This afternoon, we have that choice. This morning, we have that choice. Which way are we going to go on it? We're just going to pretend it's not happening. That's what we've done for the last 20 years. Are there things we can do technically? Well, this is the electricity system, just running through it. If we want light or refrigeration, we need electricity, we need transmission network, we need power stations, and we need the Venezuelans or the Colombians to dig the coal out of the ground for us. So we put some units on that. If we want 10 units of useful light or refrigeration, we probably need something like 50 units to go into that, depending on what light bulbs you have or what refrigerator you have. We lose 6 to 9% of the energy along the transmission and distribution network, mostly the distribution network. Power stations are 35 to 50% efficient, so most of the energy in the power station goes up the chimney, and then we have to get the coal out of the ground in Venezuela, put it on a train to the port, onto a ship, to another port, to another train, to our power station every single hour, every single day, for the next 40 years, the life of the power station. So we put all of that on, you start to see 10 units here requires 133 there. Actually, that tells us a lot what we can do. There's some real hope in this. The demand opportunities, which are all very, very, very quickly be delivered, are much quicker than these. These take 20, 30, 40 years to change. Those we can change this afternoon. We can do things today as we're going home today, as we're at work today. We can do things there straight away. Real agency, immediately. Cars, another easy one here. I'm going to whip through this one quite quickly. At the moment, any car driving past here, on average, you'll have 175 grams of carbon dioxide per kilometre as it goes past, 150 for new cars. EU plans are 130 grams for 2015. But professors, people like us, many of us here, we can buy our way out of that. We mustn't have a scheme that people like us can't, we still want to have our fast cars and our four-wheel drives. So we can buy ourselves out of that system. But the BMW are sort of, if you like those sort of things, those sort of fast-type cars that sit in queues with all the other cars. Came out in 2008, BMW 3 Series, 160 horsepower, 109 grams. 109 from the BMW, just a diesel. VW, the new Kia, Skodas, lots of cars now in that 85 to 99 category. These aren't electrical cars, these are diesel cars, not even hybrids. These are diesel cars with almost no price premium, just being more efficient. If you then add good driving practices, you could probably improve that a bit. The Audi A2 came out in 1998, had 5 seats, sits in queues, the rest of the cars, does everything else that cars normally do, and it was only 75 grams. 90% of all the vehicle kilometers traveled are traveled by cars that are less than 8 years old. So we had the guts to put policies in place that said all cars have to be as good as the BMW by the end of this year. Then by 2020, we'd have about a 40 to 50% reduction in CO2 emissions, just because of the natural rate at which these cars go through the system. If you put a scrappage scheme, you can speed that up. We reversed the occupancy trend in the last few years, from 1.3 people per car now to 1.8 as it was a few years ago. We get a 70% reduction by 2020, broadly in keeping with an outside chance of dangerous climate change, avoiding dangerous climate change. There are things we can do now, no new technologies, just policies and just us supporting them and changing our behavior. So to conclude this upbeat message, relative conservative assumptions here on the science. If science broadly works, if the cumulative emissions match with temperature, and that's broadly correct, and I think most of us would accept it is, if the industrializing, the non-OECD countries can peak their emissions by 25 to 2030, they don't think they can, but I think if at a push they could do. It's not impossible to envisage that. If there are rapid reductions in deforestation emissions, and there are some good moves in Brazil now at last on that, if we can halve the food emissions per capita by 2050, at the moment we're going the other way around, we're all trying to live like Americans. If there are no discontinuities, tipping points out there, and if Stern, the Committee on Climate Change, the International Energy Agency, if their feasible reduction rate of 3 to 4% per annum is achieved, if all of that's pulled together, then we've got virtually no chance of 2 degrees C. So the good news is we've got virtually no chance of 2 degrees C, unless we think outside the box. But we've also got a very high chance of heading towards 4 degrees C by 2050 to 2070, if not before then. And remember, the 4 degrees C could head us up to 5, 6, or 7. So that's the future choice that we have now. But I don't want to leave you with a too downbeat message. This is not meant to be, we actually put this in the paper, and surprisingly it got through the peer reviewers. This is not meant to be a message of futility, because I always get accused of being too gloom and doom. It's a wake-up call of where our rose-tinted spectacles have actually brought us. We're in 2012. We've done absolutely nothing since Rio in 1992. So real hope, if it is to rise at all, only does so if you assess, a bare assessment of the scale of the challenge we now face. Where are we in 2012, and what do we need to do? If we ask that question, then we might have some hope. And for Manchester, that's relatively clear. You need a mitigation of about 70% reduction in total emissions. That's not just partial emissions, that's total emissions. That includes the airport. It includes the goods that we're buying, some of the goods that we're buying. At the same time, all futures are high adaptation futures. We're going to have to adapt our infrastructure. So any building from today on must be able to adapt to at least a 4 degrees C or 5 degrees C warmer future. So that's what Manchester's challenge is if it wants to do something about climate change. Alternatively, it can carry on with rhetoric. And on that, I'll finish, and I'll pass you next on to John, who will actually go through the adaptation agenda issues with you. Thank you very much.